So let's start with 15 here. And this, folks, now remember, if you don't need this problem or you're not really interested in it, feel free to work on other ones. Just keep down the kind of a low din, so that like if I don't know, Hannah is trying to listen, she can hear. All right. Roger, did you still want me to?
Are you cool, like, put it on like one screen or something like that?
Yep. All right. So folks, here we go. All right. This is one of the ones, folks. If you're working with other people, just try to keep it down a little bit so you're not a distraction to others.
Oh, whatever.
It's 15. So this is one of the ones that you need both a force diagram and some words. So this would fall under the forces and other concepts rubric when you're taking the test next week. So you've got this cup of coffee on the roof, and they tell you things about the friction. They want to know the maximum acceleration for the coffee cup to stay there. Nicely, they tell us to ignore air resistance. And then they also want to know how much time to a certain speed and still keep it on the roof. That's the part B is what needs the words. Part A in your Y can be all diagrams. So let's so I think I'll do my diagram first. Weight down, normal force up, accelerating in that direction, frictional force automatically opposes motion or possible motion. All right? The larger the acceleration, the less time to So the larger the concept that isn't shown by our diagram is that second part, which the longer it's going to take you a longer time at a lower acceleration to get to that speed, right? Or however you want to say it. All right, let's do the first part. So this is part A. I'm going to use the sum of the forces equals ma. Right? Now, if you look at our diagram, there's a small problem. Look at the object. The net force is going to be in which direction? Negative direction. Which direction is the acceleration in? Positive. Can we have a net force and an acceleration in opposite directions? No. So, really what we want is we want a force applied to be in that direction, because the friction is actually on the car, and then it's creating this applied force on the cup. They're part of a Newton's third law pair, so they're equal and opposite. But we kind of take this one and say that's on the car itself, not on the cup. All right? It's the same idea with your feet, right? When you push on your feet, which way do you push? You may have to get up and walk to feel it. Which way do your muscles work? Probably not down. I don't think you go and move forward. Which way do you push? Backwards. But you move forward. That's that force pair idea, right? So the cup through friction is allowed to be pushed on by the car. Is one way to think about it. But it's going to be equal to the frictional force. So up here, I'm going to need to do both some of the forces in the Y and some of the forces in the X. The Y is pretty straightforward. Force normal minus force of gravity equals m times 0. So force normal equals force of gravity. Right? We've done that a bunch. Which equals mg, of course. Over here, really I'm going to have the force applied equals ma. But I know that force applied comes from friction, so I'm going to replace it with the frictional force equals ma. And of course, frictional force is mu force normal. So I end up with mu mg equals ma. Oh, the m's cancel out. That's good, isn't it? Because do they tell me the mass? No. Whew. Thank goodness it canceled out. Otherwise, we couldn't have done the problem. The coefficient of static friction is 0.2. So that means mu is 0.2. So 0.2. 9.81 newtons per kilogram equals a whatever a is. Something like 1.98 or something. Yep. 1.962 meters per second every second. Then we move on to part B. In part B, it asks, smallest amount of time the person can accelerate the car from rest to 15 meters a second. So I'm going to use V final equals V initial plus A delta T from our equation sheet, which if you don't have one, there are new copies in the back. Now it's substituting in, right? For my problem, it said, what's the shortest amount of time the car can accelerate from rest to 15 meters per second? And that's what I got. I hope my answers are right. Alright, here we go. Number 19. Car experiences this acceleration as it rounds a corner at a speed of this. If it's centripetal acceleration, I know it's only changing the object's direction. right? If it's not centripetal acceleration, then it might be changing its speed too. So this is one you could do some words on this, or you would do almost all words. You might do a little diagram. I'm not going to. So the centripetal acceleration just changes the car's direction. The more speed, the more acceleration, the smaller radius, the more acceleration. And then they tell me what the acceleration is. They tell me the speed. They want to know the radius. So really, I'm just using, from my equation sheet, this, rearrange it, substitute in, and I'm done. All right, so we're on to number 7. This is good. We're getting kind of a variety of different problems, right? Circular motion. This one's all about, any guesses? I get it. Something's flying through the air. Free falling. A projectile. Projectiles in free fall, yeah. So you have these pumpkins out in Denver, and they are thrown horizontally. So whenever you see horizontally and it's a projectile problem, go. Thank you. Because they just made your life easier. They've gotten rid of one vector part you'd have to shift. So that's nice of them. So they're thrown horizontally off of a high tower and trying to hit a bullseye down at the bottom. All right. Let's give it a try. So we need some words on this one. Again, and this is number 7. So I would start off with something like the pumpkins are projectiles. So in free fall. Thus, only accelerating down at 9.81 meters per second every second. Oops. There's another P in there in pumpkins. Personally, I'm going to do a little diagram. I can grab their picture, but I draw. What is it? They give me some dimensions on this. Let's see. 9 meters and 3.5. Okay, we got to make a couple choices here, folks. We need to choose where do we want to. We got to choose where do we want to put the origin? Where do we want to say is 0, 0? Who's doing this one with me? Just so I make good eye contact. Okay. So where do we want to put 0, 0? At the top, where they're launched. Okay. So 0, 0 here. Which directions do we want to call positive? Which one, right? Right, everyone said. Some people said up, some people said down.
I think we should keep it kind of like a graph. Like, because how graphs are like, if you go up, it's more positive.
It's Friday. Let's go down. Let's be daring. Ooh. And that way, if someone isn't paying attention and they just try to copy it, they'll be like all confused. So they want to know, it's always good, I always forget, what do they ask? What launch speed is needed to hit the bullseye? So let's see, some things I can think I know. If I dropped a pumpkin, would it take, and I threw another one out horizontally, would it take, which one would take longer to hit the ground? They would hit the ground at the same time. If I dropped one and I threw one. As long as I throw it horizontally, right? So, the time is going to be controlled by my y direction, and however much time I have to fall down, that's the exact same amount of time I have to move outwards. So I think my best approach would be go with the y dimension, find out how much time the pumpkin takes to drop, and then say, okay, if I have that much time, how fast do I have to move 3.5 meters in that time? So that'll be all x direction then. So I'm going to start in the y direction. And I'm going to use my good old friend, this equation. And let's see, we said he ended up at 9 meters because he starts at 0 meters. The pumpkin is who he is. But down positive, so 9 meters plus, oh, this is 0, isn't it? 0 times delta t plus 1/2 positive 9.81 meters per second squared delta t squared. Right? That's a 1/2. Oh, sigma? No, 1/2. I'm trying to write small because I want to get it all on not too much space. I know we have got some. So, I can find delta t from here, right? Yeah. Let's see what I get. Biggest mistake will be forgetting to square root.
What do we have to square root?
Well, I'm solving for t, and this is the only t term I have is t squared. So I'm going to have to make sure before I get delta t that I square root my answer. So I get 1.35457 seconds. Seems about right. So now I'm going to switch the x direction. Actually, I'm going to use my same equation. How much does it accelerate in the x direction? Anybody? Accelerate. How much does it accelerate in the x direction? 0. Because what's the only thing affecting it? Which direction is gravity point? Down. So how much is it affected horizontally? None. Nice. 0. So it's going to end up at 3.5. It's going to start at 0. It's moving at, I don't know, some speed. Call it Vx. And it's moving for 1.354571 seconds. You can find Vx. I get 2.58 meters per second. All right, so number one was the next highest requested one, and it's asking the components of this displacement vector. All right, so this is one where your y, your only thing your y would need to be would be a vector diagram. Nothing else needed. I'm actually surprised this one was asked for so often by people, but hey, it's what the class wanted, so we go with it. All right, so 610 meters long, pointing 40 degrees north of east. So let's see, I'd probably be a good idea to do a little north, east, west, and south. So 40 degrees north of east means I start east and I swing 40 degrees towards the north. So 610 meters, 40 degrees there. So I could have said 50 degrees east of north, right? And they're asking me the components of said vector. So let's call them, I'm going to call them north and east. So remember, you don't have to be working on this one with me, but be quiet enough that other people can. So north would equal, of course, 610 meters sine 40 degrees, and east would equal 610 meters cosine 40 degrees. All done. That's A and B. All done. Well, I mean, it's easy if you know what you're doing, but not. All right, so this was another highly suggested one, number 8. Again, we're back to pumpkins. Pumpkin chunkin'. So, if you've never seen this, they did a couple shows, documentaries on it. It's a really good one. Pumpkin chunkin'. You should. Yeah. Even my Boy Scout troop does it. We build trebuchets and do it. Yes. All right. So they pump again. Folks, remember, get a little bit started to hear myself sometimes. So the pumpkins are going to be projectiles, and everyone remember what angle should we launch at if we want the longest range possible? 45 degrees. Yep. So that's going to be something we're going to put here in the Y. Launch at 45 degrees for max range. Pumpkin is a projectile, thus the one diagram I'm gonna, let's see, I'm gonna include 2 diagrams. One, and that's what, 1240. And I'm also going to include that initial velocity and break it into components. right? And my approach here is like last time, where I think the y is going to control the amount of time it has because I don't see any barrier in the x direction. And then we'll use that common time. One of the differences here is we don't have as many restrictions. So you'll see how the math is going to work out, but it's the same approach as we did for the one on the tower, except we have to break up that initial velocity into horizontal and vertical first. There's one little math thing that you're going to have to do a little bit, but starting the same way. Oops, I forgot my deltas. In the y, it's going to land at 0. It's going to start at 0. Its initial velocity in the y is positive vi sine 45 degrees times t plus 1/2. I took down as negative this time. And do you notice that I have two variables in there? I've got t and v initial. So can I solve that one equation?
Yeah.
No, because I got two variables. Nice thing though is that I could divide every term by t and get rid of my squared. Because what's 0 divided by t? 0, right? So I have vi sine 45 degrees. I'm going to bring this out minus 1/2 9.81 meters per second squared t.
Did you do the negative 9.1 meters per second?
I pulled the negative out and made it minus, so that I won't screw it up if I do it on my calculator. That's the main reason. Yeah. Oh, that was the discussion we had while you guys were talking about the last song about maximum range is at 45 degrees. See, you've forgotten it already, but Roger and I had a great little conversation about it. Yeah. And then look, what does it say at the top of my Y? Can't read it, can you?
45.
For maximum range. That's where we got it. I can't go any farther there, so I might as well see what I can do in the X. Let's see, in the X, I'm going to land at 1240. I'm going to start at 0. My V initial is VI cosine 45 times T. Remember, I don't have any acceleration. Ah, cool, I've got two equations. And they both have the same two variables in them. V, I, and VI and T. So you can do some algebra now. You could put them into a solver and have it find it. But you want to come up with, at the end, what is VI. But it's all algebra now. All right? The physics is done. Now comes the algebra. Aww.
Algebra made me crazy.